Any questions about where we are so far? All right. I think I told you all I would let you know if I could have a review session this weekend. It's probably not going to happen. I'm going to be out of town all weekend, and I'm not sure what time I'm getting back on Sunday. So we're going to finish up 5-2 today. I'll have office hours today from 2 to 4 as usual. Yeah, if you need anything, definitely try to come upstairs at 2 o'clock. Otherwise, you can try to reach me over email. But I think your best bet, especially this weekend, is going to be to reach out using the Ed discussion board where you all have access to it and can all respond. So those of you who have used it, thank you. Those of you who have not, please consider doing that. But I'll be pretty quick. Any questions about that? All right. So we left off right at the tail end of this thing last time. Probably recap. We did a lot here. So I want to find the value of this definite integral. So basically, I want to try to find the area under this curve over that interval from 0 to 3. But I want to, instead of finding some finite number of intervals and finding those areas, I want to try to limit that by getting infinitely many. So that's the rationale here. We've defined a definite integral as a very special kind of Riemann sum. It has an infinite number of sub-areas in it. So I guess I want to talk about this first. I think this is the most directly applicable to, actually, this is the most important takeaway for me anyway, is are we okay where these two ideas come from? How to find this delta x, so basically the width of any given interval, and how to build this thing, this f of xi star. Let's say this, can someone tell me how we got the delta x is equal to 3 over n for this specific case? Sebastian?
So we subtracted 3 minus 15.
What are the 3 and 0 come from? Good. Good. Yeah, why did we divide by n? Right. So yeah, my full interval is 3 units long. And if I have n interval, n sub-interval, get an equal piece of that, it'll be 3 over n. I am taking samples at right endpoints that I didn't write down. Probably mention out loud, but so right endpoints. Come on. All right, so we're sampling at right endpoints, and all those individual values of x, we're going to evaluate the function at those, and did a lot of algebraic manipulation to wind up with this limit we have. Does anybody need anything cleared up about how we wound up here before we get this exact area? Go ahead, Jordan. I star. Okay, so let's go to the beginning. I is basically what you have is this, and I'm kind of running out of space, but try to find it like this. I is some variable. I leads us to x sub I. So basically, I is like it's what's called the index of this sequence of x. So I think we did the first two here. So looking at these 3 guys, first one has an I value of 1. Second one has I value of 2, I value of 3. So basically, I tells you which term in this list of x values am I looking at, and then x sub I tells you All right, I know what term I want. What is the value of that term? So you can think of x being a function of I. And then from there, once I find that value of x, then I want to find f of xi. So for any given value of I, so we're taking right endpoints. So right here, this will be x1. Actually, I should not label it there. This right here is x1, x2, x3, and then continuing that, this right here will be f of x1.
And those are what we're putting in.
Yep. And to find area, basically this f of xi star, this is your height. And this delta x is your base. So delta x is the same thing. Variable n is not for yeah, the base length of n of each little subtable, and then the height will be whatever the function is evaluated at the right end of that subinterval. So for all of these, if I wanted to draw the first few, I am not claiming that our function looks anything like this. It's just help us get our bearings. Go ahead, Gabriella. The last step where? Oh, at the very bottom. This was the part. So we talked about the. Okay, I'll just kind of start from scratch. Looking at this summation notation. So can you see my cursor on the screen up there? So looking at this summation notation, actually we should look at this one up here. What is the variable as far as this summation is concerned? I. Yeah, I is changing. N is not a variable. N basically tells me when to stop adding things up. So because of that, anything that's not I is essentially a constant. So I can pull those things out. So 81 over n to the fourth, I can remove that from the summation. And basically when I'm done adding the things together in the summation, I can just multiply it by 81 over n to the fourth. So I'm going to go back a couple of slides, and I did an example like that. It's a little more simple to get our hands on. It wasn't too far back. Here it is. So if I add the first 5 numbers together, if I want to add the first 5 multiples of 3, I can do the same result. I pull through that. So I'm taking advantage of that idea there. More real. My summations look as simple as possible. So that's why for this summation here and this summation here, all that I left inside those is the I terms, because that's the only thing I'm going to vary. And then to get from there to the step where we left, those are the parts that I'm asking you to take on faith. So that should catch us up. Are we okay with moving on now? All right, so I'll try to get this done in the space I have left without skipping too many steps. This is going to become 81 over 4. I'm going to cancel out this n squared here with 2 of the powers of n in the denominator. So this is going to become at this 81 times n plus 1 squared over 4n squared. Cancel that one out with that one, and I get minus 54 times n minus 1 over 2n. I guess I could just call minus 1. Shouldn't have. Thank you. All right. So now it's a matter of us evaluating this limit. So I am going to multiply. I'm going to multiply this one on the left. Actually, give myself some room. I'm going to multiply this fraction on the left by 1 over n squared over 1 over n squared. I'm going to multiply this one here by 1 over n times, or divided by 1 over n. And that is going to get me to a place where I can actually make my limit laws work for me. So I get 81 over 4 times 1 plus 1 over n squared over, actually that's done now, times 1, minus 27 times 1 plus 1 over n, all over 1. So in the previous step, none of my limits exist because n goes to infinity. But now all those limits exist because look at the two places where n is. What's going to happen is n goes to infinity there. What's going to happen to those 1 over n terms? They're going to go to 0. So what I'm left with is this 81 over 4 minus 27, which comes out to, awesome. Let's keep that as a fraction. So is that negative 21/4? Oh, I want 27/4. So what was the area I found when I tried to do this? 3 rectangles. I think we ended up getting 0. So obviously, but that is the exact area under the curve. Jordan?
Are we going to be doing this long? Already the original?
If you do, it won't be this. It won't be like this. I mean, this took us what? Half an hour? I cannot expect you to do something this involved. So I would be ready to. I'll say this. I promise you, you'll need to do it for the homework that's related to this. I'm not going to promise you one that'll be on the test, but if there is, it'll be manageable. I can't expect this to be. Yeah, so then you will definitely have to work with that on the homework and practice with it. But, yeah, you have questions on that? So basically what I'm trying to do is trying to get rid of these. So I have or less. Anything else on this thing? Go ahead. That's the part that I'm asking you to kind of believe me on. So yeah, there are things you can prove, and it really, I could prove this one for you in about 2 minutes. This one here is nasty. It takes a long time, but basically the sum, if I were to just to add up the first n integers, it comes out to be n times n plus 1 over 2. The other one, the I cube one, that's a lot harder to get through. But for now, the proofs are available on YouTube if you want to see them, but they're Yeah, that was probably a little mysterious. So I'm going to have to. What can be sacrificed? Oh, that's old. Oh, it's not going to let me erase the stuff I did last time. If I put it on this next slide, will that bother anybody? Okay. So this is what this is the multiplication that's kind of mysterious, right? So I have the thing on the left is squared. The thing on the right I can rewrite like this. N plus 1 squared times 1 over n squared, right? Since they're both squared, I can pull them together. I can multiply them together and then square them. And then that becomes 1 plus 1 over n all squared. Good question. All right. So now, by looking at the area. So, if we're going to do that, we should probably try to draw this out as best we can. So we're trying to find the area under the graph of a function. What is the function in this case? Basically, what I'm asking here is trying to make sure we're interpreting what the integral says we're doing. So in general, when we look at an indefinite or we look at a definite integral, what we're doing is this. We're integrating, so finding the area or summing a bunch of rectangles between 2 points, A and B, of some function with respect to x usually, with respect to some variable. So if this is the general thing, this is the specific thing. What is the function that we're actually integrating here? Yeah, the function I want to find the area underneath is 1 minus x squared. Does anyone recognize that function? I'm gonna do some algebra on it. You tell me when it looks like something you've seen. That's not cosine. It's a circle. So yeah, x squared plus y squared equals 1. That's a circle. Centered where? Centered at the origin. What's the radius? If I didn't give a big enough hint by drawing this blank graph. But basically, we're not looking at a full circle. We're looking at how much of it? A quarter of it, right? All right, so now we can find the area of this thing, right? So in time, like early next semester, you'll be able to do this integral by hand, calculate the area that way. But for now, we can just think of it in terms of geometry as a circle. How do we find the area of this kind of thing? Area equals pi r squared. We got to make sure we take a fourth of that. So what is the radius? 1. So pi times 1 squared over 4. This area is pi over 4. So this is geometry is not something that we could have used for that last example because I have no idea what kind of geometric shape. We don't have a canned formula for that shape that wasn't parabola, that cubic that we had. Jordan? It's a great question. How do I know it's not a quarter of the circle? How do I know it's not half of it? Or Thomas? 0 to 1.
0 to 1.
No, because think about what this function looks like. And when I say the function This guy here. Yeah, so if I were to look at the underside, why can't I integrate things like that? Right. So an integral only works on things that are actually functions. So for me to handle the underside, two integrals or changing my variables, things like that. Could I modify this integral? So could I modify this thing to find the area of half of the circle? How would I modify that? Right. If I change this to the integral from -1 to 1, then I am doing the entire, it's a semicircle that exists above the x-axis. So this right here, what would this area be? Pi over 2. Any questions on that? Circle. All right. Same idea. I want to evaluate as an area. So what should I do? Do a graph. So from 0 to 3, 0, 1, 2, 3. -1. All right, so got a couple of different things I'm looking at here, right? Now I want to remind you, think about how a Riemann Sum is calculated. You're below the x-axis. That's this area right here. Do this as thing. Yeah, so let's do 2. Yeah, so we do area 1, area 2. Area 1 on the left, area 2 on the right. What's the area of area 1? Almost. Right. So here I'm gonna keep this in Riemann sum notation, or like just the rationale for it. So base times height divided by 2, right? The base length is 1. The height is -1 over 2. So I get -1/2 for that area. All right, area 2, all positive. Again, base times height over 2 is going to be 2 times 2 over 2. It's 2. So what is the value of this integral? One-half? 1.5, yeah. Let's more detail here. 2 plus minus 1/2 equals 3x. What? So whenever you have like, yeah, so a phrase that I used last time. Find area, which implies that my areas don't have to be positive, even though in geometry that's kind of meaningless. In the case of Riemann sums, and when you're on a coordinate plane like this, there are negative positions, so you can have negative areas. Any questions? All right. I want to do one more midpoint example because I feel like the way that I treated them the other day probably caused more confusion than it deserved to. So let's look at this function here. And just to be clear, what is the function I'm looking at here? 1/x. What's the interval I'm going to look at? Looking at a equals 1, b equals 2. I'm going to say equal subintervals. So how long is each one of my subintervals going to be? I heard it mumbled. 1/5. More importantly, how do we get 1/5? Right. So the full length of the interval is 2 minus 1, 1. I'm going to divide each into an equal fifth share. And just to make this easier to do calculations with, we'll call that 0.2. So now let's do this. How many of these x values do I need? I heard 4 and I heard 5. And I blew it by kept writing after x sub 4. Why do we need 5? 5 intervals, right? So 5 subintervals. How many sample points do I need for each one? Exactly 1. So it's not about getting every endpoint involved. It's about getting 1 sample point per interval. So I want midpoints. Because I want midpoints, what is my first value of x going to be that I sample at? 1/10. How'd you get 1/10? Right. For the first one is 0.1. Maybe we would benefit from a picture at this point. So 1/x sort of looks like this. I'm going from 1 to 2. Ignore the fact that this is not scale at all. 2, 6, 8. So 1.2, 1.4, 1.6, 1.8, and I think I just realized that our first x value is not 0.1. Not 0.2. It's 1.1. So the first x value is 0.1 from the beginning. But our interval does not begin at 0 this time. So because of that, I need 1 plus 0.2/2. That gives us 1.1. Any questions on where we got that? Oh, go ahead, Gabrielle. Mm-hmm. So yeah, I'm dividing by 2 because I want the midpoint. Where did I get that 0.2 from? That's the change in x. So basically, every one of these little subintervals is 0.2 units wide. I want to start from the left of each interval, but then I want to go half of an interval to the right of that, which is how I got 1.1. Based on that, where is x2 going to be? 1.3. Is it a coincidence that these two things are a delta x apart from each other? No, that has to be. Based on that, where's the next one? 0.5, 1.7, 1.9. Go ahead, Sebastian. Yeah, I do see what you mean. So this is going to be 1.1, no, 1.2 plus 0.2/2. Why is it 1.2? Right. So let me unpack this a little more. This interval right here is going to be, so what's the little subinterval that begins at x1 and ends at x2? 1 to 1.2. This one's going to be, there you go. So yeah, basically, I'm only going to have a few of these though. 1.6 to 1.8. And then the next one that I think I'm off. Was that? Well, I mean, we always need to know where the left end of the subinterval is. So for the first ones, it's at 1. I don't want to sample it left. I need to know where the left is to figure out where I actually want to sample from. Oh, I see. Okay, yeah, you're right. Gordon, you have a question?
Well, yeah, I just want to say, like, I think it's easier to think about it. Once we're just finding what's in between.
Yeah, I'll give an idea here. So, I mean, here's a specific one. I'll just do 1.4 to 1.6. And then x3 is right here in the middle. Is at 1.5. So yeah, no matter where you're sampling, you need to know kind of what the boundaries of the subintervals are. And I think it's probably really helpful to draw these things out. All right, so now that we have done this, can we start finding this? Can we start evaluating this Riemann sum? So this is not an integral. I mean, it's going to be a bad estimate for an integral because I'm only using 5 rectangles. So now it's just a matter of adding these things together. Keeping in mind that our function is 1 over x, I'm going to do this, 1 over xi star times delta x. So I'm going to have 1 over 1.1 times 0.2 plus 1 over 1.3. And if someone could start calculating this out while I'm writing out the actual calculation I'm describing. Exactly 5? That seems too high. It's 0.693? 0.692. All right, that sounds more reasonable. But I equals 1?
Yeah.
No, so I really, I think every time I've done with I equals 1. Yeah. And this, but it's but really, that has nothing to do with it. It's just, what do I want the first kind of like location, the first address of the sequence to be? Well, the I equals 1 has nothing to do with it. Yeah, so I mean, I put in like I equals 0, but then what is it? Right. Anything else about this one? So let's go over some properties of definite integrals. So one thing we haven't really talked about, but when you're doing integrals, negative and positive positions. So because of that, what's the difference between the left-hand side? Something subtle. Well, one is the exact opposite of the other. Like one is the negative. But beyond that, what did I change? Yeah, the B and the A are flipped, right? So every interval we've done, we work around the right. We started at lesser boundary. As we go on the lesser boundary, basically, this is what I'm saying. If you reverse the interval, you get the same magnitude, but it'll be the opposite sign. So, for example, what would this be equal to? We found something very similar to it just a bit ago. What was the area of the quarter circle? Pi over 4. So what would this integral be equal to? Negative pi over 4. Because in this case, all my delta x's are going to be negative because I'm moving from 1 to 0. How about this interval? What would we expect the area to be underneath this curve on this interval? Why 0? It's just a single point there. I have no base width to gather any area, to accumulate anything. How about this one? I'm assuming C is a constant. Not just C. Let me give a concrete example here. What if it was like I'm integrating from 1 to 9 and I'm integrating the function 2? How'd you get 18? 2 times 9. Yes, you're close. I don't think it would be 18. Not negative 18. I'm starting at 1 and going to 9. It's going to be positive. I heard 16. How'd you get that? Right. So remember, if we think about this in terms of area, if I go from 1 to 9 and the height is a constant 2, the height of this rectangle is 2. What's the base? Yeah, the base is 8, height is 2. That's an area of 16. Can we generalize that then? How do we, if I'm integrating over an interval of some constant, what's that going to come out to be? Yeah, it's just the height, which is C, times the length of the full interval, which is B minus A. Moving on. We can treat multiplicative constants the same way we did for, remember, a definite integral is a Riemann sum. It's just a very specific kind of it. So if I have this situation here, I can say this is equal to this integral b from a to b of the function f of x dx. I can take the integral first and then multiply it by a constant c. Sums and differences act kind of the way you would expect from derivatives. From other summation notations we've done, we can say this: the integral from a to b. So if this integral on the left equals this, the integral of f of x dx plus or minus the integral of g of x dx. So just like when you're taking derivatives, I mean, not that these are the same thing, but go ahead. You.
find the verse.
Yeah. So basically what I'm doing here is I'll try to give a concrete example. Oh, I did give a concrete example here. Now I'm going from 1 to 0. If I were to think about my delta x in this case, it's still going to have like a magnitude of 1 over n, except now I'm going from right to left. So if we were to set this up using a Riemann sum, you would have a base length that is always negative. But because the function is still f of x equals radical 1 minus x squared, and we saw from the graph of that all those y values are positive. So you're going to have, you're multiplying a bunch of positive heights by a bunch of negative lengths. So that's what we got the same, we're still getting the pi over 4 that we were expecting. So there's the exact opposite. Any questions? Any other questions before we move on? No, it's not a dumb question at all. In fact, let me apply that to our rectangle here. Are we okay with thinking of these things as areas? That's a common way to think about integrals. But if I were to find the area of this rectangle, what's the height of it? What's the base length? It's not 1. It's that line, right? It has no thickness. So really what our integral is doing is accumulating a bunch of, you can think about an area that really could be a lot like this. You're accumulating some kind of quantity as this interval sweeps across this whole. A separation in whatever your base quantity is. All right, so this integral here, this is not something you know how to do yet, but based on things we've done and the laws we have, we can pull this apart and make it more digestible. So if I use that sum identity, I can do this. I'm going to split this up into 2 separate integrals. The integral of 4 from 1 to 0, and the integral from 0 to 1 of 3x squared dx. Can you now just evaluate that integral on the left? I'm integrating a constant. Yeah, so that one's just going to be 4 times 1 minus 0. I'll leave that in long form for now. But now I have this integral of 3x squared, which I know is going to be the same thing as triple the integral of just x squared dx from 0 to 1. And we have done this before. And if you don't remember what the integral, so this is the first integral we did exactly together on Monday or maybe Wednesday. But the integral from 0 to 1 of this function x squared is 1/3. If you need more detail on that, yeah, flip back in your notes a couple of pages, but we did that. So this full integral comes out to be 4 plus 3 times 1/3, which is equal to 5. Again, this is something that in very short time you'll be able to do just without having to call back on other stuff or even break it down really, but this area under that curve is equal to 5. Any questions there on how I built that out? All right. One more thing I got to show you. So we know that the integral from 0 to 10 of this function is 17, and the integral from 0 to 8 is 12. What can we say about this one here? What is the integral from 8 to 10 of f of x dx? Think about that while I draw a picture. So I'm going from 0 to 10. So what do I know this big area is right here? 17, right? What other areas do I know? So from 0 to 8, so if I, a better way to represent this. So I know this little area right here is 12, right? No, this is 12. And I know the whole thing is 17.
Integral 5?
Integral 5. So basically this allows us to split either, we'll do this in two different directions. Split up intervals, or we can take two intervals that, I can add them together to get a new integral. So modeling this in terms of area, are we okay with this idea that the integral of this function from 8 to 10 is 5? So let's end by generalizing that. So I got the integral from a to b of f of x dx plus the integral from b to c of f of x dx. And I simplify this in some way. The integral from a to c of f of x dx. This is essentially the, without seeing this. So I'm going to integrate from a to b and also integrate from b to c. So this area right here is just going to be the integral from a to b of f of x dx. This is the integral from b to c of f of x dx. Or if you have the means, you can integrate both all at once. Any questions on that idea and how, and the kind of the one example we applied it? All right. That's all I have. I'll stick around to answer some questions if you want. I definitely can. Otherwise, I will see you all Monday. All of 4 and then 5, 1, 5, 2. Yes. Similar format. I'm going to have
Is it going to be more focused on the pre-response like it was last time? Okay.
That's so I know that the full length of so it's not even because it feels like it's not going to be
If we're gonna be able to use that. Oh, okay, no problem.
Right?
No worries, I just want to make sure that if there was one, I didn't. Thank you.
You too?